So in this video I'm going to show you some servo control, particularly how to make multiple servos move together, start and stop together, but also how to make some servos move very smoothly, so accelerate smoothly and then decelerate, which gives robots and mechanisms a more human-like approach. So you can see both motors working simultaneously. The one on the right is moving twice as far as the one on the left, so I'll explain that in a bit more detail.
We can control the speed of a servo motor by allowing it to move from one position to another over a specific time. So example, if we have a motor which we want it to move from 20 degrees up to 90 degrees over a time of 5 seconds, then what we have is an equation which states that the angle of the servo motor, so theta, with respect to time, is equal to the starting angle, so in our case it was 20 degrees, plus a value a times the value of time itself, so t would go from 0 up to 5, and a will be the starting angle, theta naught, 20, minus the ending angle, which would be theta naught, which is 90, minus theta s, which is the starting angle, which is 20, divided by tf, where tf is the total move time. And that's actually the speed of the servo. So if we have the total angle moved divided by time, that's the servo speed. So A is actually the servo speed. So it's the end angle, 90, minus the start angle, 20, divided by the final time. So graphically, it would look like this. If it's going to go faster, then this graph would be steeper. To make it go faster, you would drive it over a shorter period of time. So what I've done is I've written some code on a Arduino, which allows a servo motor to move with that period of time. But what I've also done is I've created this code to drive two servo motors, so they can both move to different angles but over the same period of time. So what you get is two servo motors which will both start and stop at the same period of time. So the main code that I'm calling is within this loop here. So theta 1 is a function which calculates the angle of servo 1, and theta 2 is a function which calculates the angle of servo 2. So you can see here that the first servo is going from 0 to 90 over a period of 10 seconds, and the second servo is going from 0 to 180 degrees over a period of 10 seconds. So they should both move at the same time, but the second one should go twice as fast as the first one because it has to cover more distance. It goes 0 to 180. And what I've also got is that's moving one way, and then the state of 2 is moving back. So the first servo is going from 90 to 0 in just 4 seconds, and the second servo is going from 180 to 0 in 4 seconds as well. And then this bit of code here just switches the state, so whether it's going out one way or coming back the other. So it should move back and forth like windscreen wiper motors. And then I'm using the servo right, and then I right the angle. Now I noticed that one of the servos was going in the opposite direction, so I've just made it 180 degrees minus the angle, which just makes it turn in the correct way. So the code to do that uses millis. Now millis is a timer in the Arduino which just counts milliseconds. So this is the function that I call. And you can see that the function has theta s, starting angle, theta e, end angle, and tf, the total move time. And what I do is, when the function first starts, is I set ts to be equal to millis, because millis is just a free running timer, so it can be any huge number. It's ever since the Arduino has been switched on. And then I calculate a, which is the end angle minus the starting angle divided by the total move time. Then I do a conversion to find the actual time in seconds, and that's taken from the current millisecond clock subtracted from the time when I first called the function in the initial state, in the initial sense. And then what I do is this variable is equal to the starting angle plus a0 that we've calculated times t time. So that's the linear equation that I showed you in this document, which is this one here. So that's basically that realized in a piece of code. And it returns the value, and then that value is written to the servo motor, where we're using the servo library. So I just write the angle, so that goes between 0 and 90. And this one goes between 0 and 180. So the servo library is servo.h, and the calculations are done for the two separate servos. So I've repeated the function twice. There's probably a nicer way of doing this, but that's for servo 1, and it's exactly the same function for servo 2. The reason why I've used two separate functions is because I've got some static variables in here. In other words, they are stored in between function calls, but they are particular for the angles of the servo that I'm addressing. So I'll show you this in action.
Here we have the two servo motors. So the one on the left is going 0 to 90, and the one on the right is going 0 to 180. And in the first instance, it's going between 0 and 90 or 0 and 180 in 10 seconds. So because they're both doing it in 10 seconds, the one on the left is going half the speed of the one on the right. And when they're going back, then they're going their full width in 4 seconds. So you can see that they're moving simultaneously. So this is often used in robotics, where the one of the servos might be a robot. It might be controlling a robot arm. So the one on the left might be the shoulder of the robot, and the one on the right might be the elbow of the robot. And both of these motors are connected together through the links of a robot. And what happens is you want your robot joints to all move simultaneously, to all start and stop at the same time. So just using this piece of code, you just set the time that you want as an index that you want the servo motors to move to, and hence they'll move together.
Moving on from linear control, we can actually make our motors move in a much smoother way. So if you had to move the motor from one position to another, really you'd like your motor to slowly accelerate, reach its maximum velocity, and then decelerate as it gets there. So as an example, moving from 20 to 90 degrees rather than a straight line over 5 seconds, we can have this S curve. So this is position over time, and you can see that it's slowly picking up speed, and I get at 2.5 seconds, so half the time it's moving at the maximum speed, and then it slowly starts to slow down, so it starts and stops much more smoothly. So if you've got a robot arm that's carrying a large mass, it's much better and more natural to carry it with a smoother trajectory of motion rather than stopping it and starting at maximum speed. So this curve is a cubic polynomial. So it has a cube term in it, which can specify how that line looks. And the equation for a cubic polynomial is here. So we have a0 plus a1 times t plus a2 times t squared plus a3 times t cubed. Now t is time, and the a's are some constants that we need to calculate. So I've made it quite easy. There is a way of proving what these values need to be, but a0 is 0, sorry, it's not A naught is the starting angle. So it's theta, no it's not, it's the final angle, so it's theta naught, the final angle. A1 is 0. A2 is 3 divided by the total time squared multiplied by the total angle which is subtended, so the final angle minus the starting angle. And actually going back, A naught is the starting angle, starting position. And A3 is minus 2 over the total time cubed times the total movement angle, so that's the final angle minus the starting angle. And you can find your TF, well, it could be distance over the maximum velocity. You could make it a longer value if you want your motors to go slowly. You could make it a shorter value if you want your motors to go quickly. But if you use time as an index and you're controlling as many servo motors as you like, then they will all start and stop simultaneously over the same time period. So let's say you've got one motor which is moving between 0 and 10 degrees and another motor which is moving between 20 and 90 degrees, then the one moving from 0 to 10 degrees will move over the same period of time. It will start and stop at the same period of time as the joint that's moving further. Of course, the joint that's moving further will move faster. Just looking at the velocity of one of these joints, if a joint is moving from 20 to 90 degrees, the velocity is plotted on this pink line here, and you can see that it gets to its maximum velocity at half of the total movement time. So 2.5 seconds, it's moving at maximum velocity. After that time, the velocity starts to reduce. So the velocity increases, maximum velocity, and then the velocity reduces. The acceleration is maximum when the joint first starts to move, and at half of the time, when it's at maximum velocity, it's almost free falling, if you like. So the acceleration is 0, and then the acceleration becomes negative as the joint starts to slow down. So just having a look at the, I'll just put the equation back on the screen again. So this is the main equation. So this can be realized in a bit of Arduino code, which is here. So this value here, θ, is equal to A0 plus A1 times t plus A2 times t, that's t squared, plus A3 times t times t times t, so that's t cubed. To calculate these constants, A0, A1, etc., there's a bit of code here. So you can see A0 is the starting angle, theta s. A1 is always 0. We could just leave it out if you wanted to. A2 is 3 divided by t, the total time squared, multiplied by the starting angle minus the ending angle minus the starting angle, etc. And then I calculate t from the millis, just like I did earlier. So I've replicated this twice, and I've given it to, it's the same angles that you saw in the linear motion, so 90 and 180. This time it's moving 3 seconds to go out, and then it's moving back, but over 10 seconds. So we can see that moving.
So here we have it moving out in the 3 seconds, and then it's moving back over 10 seconds. What you might notice about these motors is they're moving a lot smoother. So when it first starts, it's going quite slow. It reaches a maximum speed and then it slows down. So it gives it a bit more of a human-looking approach to it. It speeds up fastest and then slows down to slowest. The servo motors have got a little bit of a glitch in them, so they're not 100% smooth, but normally, if they're nice, fresh servo motors, they should be. And you can see that they're moving simultaneously, reaching a maximum speed at the same time, and then slowing down and stopping at the same time as well.
can also use this to control the speed of a motor. So it doesn't have to be just controlling position. So what I'm just going to show you here is that I've got a robot and I've got some libraries for the robot. And one of the libraries is a command that allows it to drive, and that drive is a speed. Drive a speed of 0 makes a robot stop. Drive of 1 makes it the motors turn and it drives at 1 meter per second, and drive of -1 makes it reverse at 1 meter per second, and you can drive at 0.5, which makes it drive at half a meter per second, etc. What I'm doing now is I've just altered the program. I've got some other library folders functions here called read button, so you'll see this in the next clip. And what I do is the whole idea is to make the robot speed up very smoothly and then slow down very smoothly. The robot speeds up from 0 meter per second to 1 meter per second over a time of 5 seconds. And then when I press the second button, the robot slows down from 1 meter per second down to 0 meters per second over a period of 10 seconds. So that's calling exactly the same function. So it doesn't care whether it's an angle to move to, or a linear position, or the speed of a motor, or the brightness of a light. It can all be used in a very flexible manner in that way. So I'll show you in the...
So you can see the effects of this program. On this screen I've got the speed of the motors, and it goes between 0 and 1 is maximum speed, relates to 1 meter per second. So this is the speed of the motors in meters per second, or the speed of the vehicle in meters per second, I should say. And I've got it connected to a program, so if I press button 1 it speeds up in 5 seconds, and if I press number 2 it slows down over 10 seconds. So if I press button 1 you can see the speed and you'll hear the motors as well. So that's gone up to full speed in 5 seconds. When I press this one it'll slow down over 10 seconds. And you can just hear the motors although the motor stopped, you could hear the pulse width modulation of the motors still trying to move. So I'll just do this again and you can actually see the motors this time. So pressing 1. And then pressing button 2.